Hello, my name is Christian, and this is a continuation of the previous workshop. Here, we're going to perform a topometry optimization. We want to use topometry optimization to tell us where the core thickness should be the highest so that we have a lightweight composite panel while satisfying buckling load constraints. Now, this is part 2 of a 3-part series. Right now, think of this workshop as a workshop to generate data. Once we have this data, we'll go ahead and start a new workshop where we're going to use that data to create a core that has a variable thickness, or rather, I think this diagram does a better job. We're going to create a core where the thickness is allowed to vary in different regions of the curved panel. So let's go ahead and get started with this workshop. Here on this table, if you recall from the previous video, I went ahead and documented the results of that core thickness optimization. So that would be this column here. This is where we're starting at. So in the end of this presentation, you're going to see that topometry optimization can yield a more lightweight composite where the thickness of the core is allowed to vary, while at the same time we come close to satisfying the buckling load constraint. And I'll give you some more comments regarding this later on. Now, we're still dealing with the same analysis model, fixed on one edge, and then we have a load on the other edge. Now let's talk about the problem statement. As always, please take a few moments to write out what your problem statement is. It does not have to be exact at the beginning. It could be a very rough draft. But as you continue to evolve your problem statement, you're going to get more and more specific. For example, if you want to constrain the displacement of a point, your problem statement should say, I want to constrain maybe the z component of displacement for grid or node 101. These are the sorts of details that should be included in your problem statement. And here for this problem statement, let's discuss what we have. So we're going to let the entire core vary in thickness. So we're going to say that for layer 5, and since it's symmetric, it's going to automatically update layer 6. We're going to let the thickness vary for each individual element. And we're going to let the core vary between very small values of 0.001 millimeters and 25 millimeters. Now, 2 comments about this. Number 1, remember, we're only dealing with half, or rather the pcomp entry. I think I still have that pcomp entry. Remember that the pcomp entry is using the symmetry option, so we only defined half the composite here. So even though the core might be 10 millimeters now in the pcomp entry, internally Nastran is going to double this composite. It's going to mirror this composite. So the core is actually 20 millimeters for this example. So this is why here the actual total core thickness upper bound is 50 millimeters. And the lower bound is going to be double, so 0.002. And again, this is why even though we're dealing with layer 5, internally we're also optimizing layer 6. Let's see, and here we're going to be building what's called a tomvar entry to specify that we want the thickness to vary for each individual element in the composite panel. And the objective and the constraints are the same as before. We want to minimize the weight while making sure that the buckling load factor is greater than 1. Now, we are going to be using the truss region in this example. When it comes to buckling load factor optimization, you will, in many situations, get this weird behavior where your objective, your normalized constraints, and your design variables are sort of jumping up and down. The appendix of this workshop goes into more discussion why this is happening. I will not go over this in this workshop, but know that if you refer to the appendix, you can read up more on why this is happening. Here, what I'm going to say is that to prevent this strange behavior, we're going to employ what's called the truss region in this example. So you'll see me use that later on. And let's see. Anything else I want to go over? No. So let's go ahead and get started. So as always, I'm here to support you. If you ever have a question on optimization, or you want to learn how to use machine learning for finite element analysis or CFD, if you want access to any of the tools you see here today, you're more than welcome to contact me here at this email address that's here on the screen. Now, today we'll be using the Sol 200 web app. We'll be primarily using the Sol 200 part of the web app, which allows you to perform simple optimization. Also know that the web app has automated machine learning capabilities. This is really neat stuff. You can let the machine learning algorithm automatically adjust your structure for you. That's also included in this package. We have multi-model optimization capabilities. If you want to build plots with Nastran data, if you're someone who's using Excel and the F06 file to manually create plots, I definitely encourage you to look at the HDF5 Explorer to automatically build your plots. And there are some other capabilities that are worth looking out for in the software. So let's go ahead and get started. I'm basically continuing on from the previous example. If you want to start with the same files I have, you can refer to the user's guide, go to the composite set of tutorials, look for the composite panel tutorials, and if you look at phase C, click on this link, starting PDF files link, and this will download all the files that I'm working with in today's tutorial. So let's go ahead and get started. So we'll go to the home page. And then if you recall, in the last tutorial, we did a constant core thickness optimization. And after the core thickness optimization, we had this final bulk data file created for us. So if you look here, the new updated thickness was 5 millimeters. So here, what I'm going to do is I'm going to copy the original starting file for topometry. So let's go ahead and say topometry. I'm going to open that bulk data file, and I'm going to make an adjustment here. So before, the core thickness was 10 millimeters, but after we performed the constant core thickness optimization in the previous tutorial, we found out that the optimal thickness was 5 millimeters. So I'm just making that adjustment here. We're going to go ahead and take that new bulk data file with the 5 millimeter core thickness, and we're going to upload it to the optimization web app. Now, here it's very important. Make sure that when you click on variables, you click on topometry. Now, I've done this multiple times where I accidentally create a size variable. So make sure you click on topometry, then go here, click on thickness, or type or search for thickness. For the fifth layer, which is the core, click on the plus icon, and then this is where you can go ahead and configure the tomvar entries. So here, make sure that the right side of the screen reads tomvar. The lower bound, I'll purposely have it at 0.001. Now, the reason I'm letting the core thickness be very small is because of the following. If the core takes on a very small value, that region is a potential region where you can maybe remove the core. And I'll make more comments about this in a few moments. Now, for the objective, let's see what we have. We want to minimize the weight, so let's go ahead and click on objective, and we'll click on the plus icon to build this weight response that we want to minimize. Let's go to constraints. We'll go and look for buckling, and here I should be looking for buckling here. We'll click on the plus icon. We'll go ahead and constrain the first buckling load. And we'll say that the buckling load factor should always be greater than 1. We'll go on to the subcases section. And like I mentioned in the previous tutorial, this is a multidisciplinary optimization where the first subcase is statics and the second subcase is buckling. Once we've configured the analysis for subcase 1 and 2, we'll go ahead and assign the buckling constraint to the buckling subcase 2. Now, remember, there is a really odd behavior that happens sometimes with buckling optimization. So here, to avoid this really odd behavior, I'm going to use a very convenient capability called the trust region. And then we'll go ahead and export the files and we'll go ahead and start this new optimization. Now, you might be asking, what is the trust region? I would recommend that you refer to this appendix in this workshop. The question is, why use trust region? There is another workshop here. Before I go ahead and talk about that, let me take the downloaded zip file and let me call it Topometry optimization. And we'll go ahead and extract and start this optimization. So what is the trust region? I will not go into great detail about the trust region. There's a lot of documentation here that can explain what this capability is. I'll just explain what the benefits of the trust region are. So first, let me find this other example that has more information about the trust region. I believe it's this other buckling example. And let's go ahead and see what the appendix looks like in this example. Okay, perfect. So if you look at this workshop, buckling optimization of a cantilever beam, if you go to the appendix, the appendix will do a better job of explaining what the trust region is, technically what it's doing in the background and all that good stuff. So I would refer you to this other example that talks in more detail regarding the trust region. Also, this other workshop talks about the negative buckling shapes that I mentioned earlier in this example. Here, this will explain in more detail why you could possibly get negative buckling load factors. Now, let's see what else. Let me explain the benefits. So the trust region should be used in the following way. If you have buckling optimization, use the trust region. If that does not work, try again with no trust region. For other size optimization, size and topometry optimization, do not use trust region. First, run your optimization with no trust region. Once you successfully get an optimization result, if you have time, run with the trust region. The reason is because the optimization might actually go faster with the trust region. And I'll give you an example. If your optimization took a horribly long 50 design cycles, in some cases when you use the trust region, you might converge after 10 or 15 design cycles. Now, this is of course problem dependent. This is why I recommend that you first run your optimization with no trust region. Once that works successfully, run the optimization a second time with the trust region on. If you get a faster optimization, then you know that for your future optimizations, you could just leave the trust region on and get really fast optimizations. So let's go ahead and look at the results. And here we maxed out the number of design cycles, but this is okay. Let me go ahead and open up the F06 file. And let's go ahead and look at what the buckling load factor is. Actually, we don't have to. We can just look here. Okay, perfect. So two things about topometry optimization. Typically, they require more design cycles to converge. I think in my notes, I use 60 design cycles. So let me go ahead and look at... Right, I see that. Right. Okay. So in my notes, I use a maximum of 60 design cycles. It seems like I converge after 26 design cycles. And you know what? Maybe I'll do that. I'll re-download this optimization with 60 design cycles as the maximum. And then I'll run that topometry optimization. Now, what I want to do right now is say that even though we exceeded the maximum number of design cycles, we can still use the results of the topometry optimization. So here, let me do this. Let me open Patron with the first set of results. So let's go ahead and open Patron here. And then I'll open a second Patron window in a moment. So let's go ahead and minimize some of these windows. And remember, I'm trying to open 2 Patron sessions right now so we can do some comparison. Now, in this first Patron window, we're going to display the results of that optimization that hit the maximum number of design cycles. So we'll go ahead and compare the results in a moment. So let me just get Patron configured here on the left and right. And then I think I might have to do this again. All right, let me do this again. So let's go ahead and open Patron here on the left. And then we'll go ahead and open Patron here on the right. And then I should note that in this other window, we did actually converge. So let's go ahead and import the result for both of these topometry optimizations, the one that did not converge and the one that did converge. And the message here is that even though you did not converge, you can still use the results to influence your decision making. So let's go ahead and import the model. And then I'll do this for the other Patron session. And what you want to import right now are the .ply files. So whenever you perform a topometry optimization, you get these .ply files. So basically, this is the thickness distribution for the core. And we want to review this right now. So let's go ahead and go to Tools, Design Study, Post-Process, and then click on Select Results File, and navigate to Directory 3, which is the job that did not converge. Now, here in the file name, type in asterisk dot and press enter. And then this will show you all the files in that directory. Click model.ply0005, click OK, and click apply. And now, when you go to the results section, and you click on fringe, and you select these different results here, click apply, this is what the thickness distribution looks so far in this failed optimization run. And it's failed because it hit the maximum number of design cycles. On the right side, I'm going to repeat the process, but I'm going to do this for the optimization that actually converged. So let's go ahead and locate the 4th directory. We're going to go ahead and type in asterisk decimal point, click model.ply0005, and click apply. And we'll go to the results. And one thing I don't like, I rarely ever like to look at the average results. They're sometimes a little misleading. So here what I'm going to do is click on the first, second, third, and fourth icon. I'm going to turn off averaging here with the domain equal to none, and then I'll click apply. So these values that you see here, these are better aligning with the values that you see here in the file. Sometimes when you average, you can accidentally mislead yourself, and that's one of the reasons why I personally don't like to use the averaging. Here's section 1. I don't know what the name is for this. It's either a button, an icon, a tab 1, icon 2, 3, and 4. Click on none, and then we'll go here. Perfect. So now let's go ahead and look at the results. Number 1, let's look at what the buckling load factors were for the failed optimization and the successful converged optimization. So let's go ahead and open this in another window. So here on the left is the failed optimization. And we know it's failed because here you'll see in the message it says run terminated due to maximum number of design cycles. If we go to the other successful optimization, if we go to the very bottom, it should say something like run terminated due to hard convergence. So this is the successful optimization. If we scroll up a little, we can actually look at what the maximum buckling load factors are. So here, you see that number 1, these values for the buckling load factors are actually less than the lower bound of 1.0. So we're slightly violating the buckling load factor constraint. But this is okay. We just want to get close to 1.0. And if we look at the results, you'll see that the results are yielding the same conclusion. The results are telling me this. Let me go ahead and take a screenshot of both of these solutions. And let me go to the PowerPoint and copy this here. When we go to the next tutorial, we're going to use the results of the topometry optimization to create a new variable thickness core. And even though this optimization failed, we still get the same conclusion as the optimization that succeeded. And this is that same conclusion. Here we're being told that the core should be thick here. The core should also be thick here. That's the conclusion. That's the conclusion in both of these optimizations where one failed and one succeeded. So even though you might spend an hour, 3 or 5 hours to do your topometry optimization, you might think that, oh no, I ran out of design cycles. That's okay. You do not have to run the optimization, or rather the topometry optimization, all over again. You can still use the same solution to influence your decision making. So let's go ahead and now look back at the workshop and see if that's pretty much everything I needed so far. Right, okay, let me do this. I don't know if I documented that here. I guess not. So it would be worth looking at. Right, let me open the previous tutorial file. And let me just show you where we're at with all these different workshops. So let me start closing Patreon since I no longer need it. Let me actually start closing some of these windows in preparation for the next tutorial. I think it was workshop B, I believe. No. I'm getting my workshops mixed up here. I'm looking for this table. Perfect. Okay. So let me actually look at what the final mass was. The final mass was 2.97, which is what I get here. Okay, perfect. So this is the mass that we reached in this tutorial with the successful converged topometry optimization. Even though the buckling load factor is slightly less than 1.0, that's okay. The goal of this workshop was mainly to get data on where we need to place the thickest core. In the next workshop, we're now going to configure a variable thickness core. So definitely be sure to watch that next workshop. And let me make sure if there's something else I'm forgetting to mention. Nope, that's pretty much it. I think I'll stop here and then I'll see you in the next tutorial. Thank you.